Hi everybody, today we're going to talk about electrochemical cells. Another word for electrochemical cells is batteries. So a battery is basically a redox reaction. So it's a chemical reaction that produces electricity. In order to make an electrochemical cell or a battery, you need four things. And so the first thing that you need is having two metals. So if you look at a AA battery or something, you'll find that you have two ends of the battery. One is labeled as positive, one is labeled as negative, and it's usually a metallic piece there. And so you need those two metals, and they are called electrodes, the two electrodes of the battery. Your electrodes, one of them is called the anode and the other one is called the cathode. The anode is the electrode where oxidation occurs. The cathode is the electrode where reduction occurs. One way to remember that is A and O, C and R. A comes before C in the alphabet, O comes before R in the alphabet. So A and O go together because they come first, compared to C and R, they come last. Another way to remember it is that A and O are both vowels, whereas C and R are both consonants. So you always need to remember that anode is where oxidation happens, cathode is where reduction happens. Hopefully anode and cathode, those two words remind you of another two words. Anode sounds like anion, cathode sounds like cation. Anions are negative, so the anode is the negative electrode, and cathode sounds like positive, like cation, which is positive, so that's the positive electrode. So if you want to build an electrochemical cell, if you want to draw it, you would need to take those two metals and put them in containers or in beakers or something like that. So here is my container or beaker for the anode. Here's my cathode, and according to tradition, we always put the anode on the left and the cathode on the right, just like you would normally write them alphabetically, A and then C. So in here we put a piece of metal, and here we put another piece of metal. Remember that anode is where oxidation happens, and it's negative. Cathode is where reduction happens, and it's positive. So we need to get the two metals. In this case, in the example that we're doing, we are going to use silver and magnesium as our electrodes. Those are the two pieces of metals that we have. So we need to figure out, do we put the silver here or the magnesium? And to figure that out, you need to figure out which one is going to be oxidized and which one is going to be reduced. So in order to know that, you need to look at something called reduction potentials. So that's on the next page in your packet here. These are called reduction potentials. And the word reduction means gaining of electrons. Remember, Leo goes Gur. The word potential, like if you have high potential for something, that means you are likely to do it or you have the ability to do it. So reduction potential is the likelihood or the ability to be reduced to gain electrons. And this table is has a whole bunch of reduction equations here, and I know that these are reduction equations because there's electrons being gained or added. And so reduction potential, its symbol is capital E, and it's measured in volts. Those are the units for it. So what they did was they picked an element, and they said that's going to be our standard. So reduction potentials are all relative to each other. And so they picked hydrogen as the standard here, and they said the reduction of hydrogen from H plus to H2 is going to be set at 0. That's going to be our standard, so it's going to be 0. And they figured out the likelihood or the ability of other elements to be reduced compared to hydrogen. So if they are more likely to be reduced, they'd have positive values. If they are less likely to be reduced than hydrogen, then they have negative values. So the table is set up, this specific table is set up so that the highest numbers are at the top and the numbers decrease until the bottom is the lowest numbers. So the highest numbers, that means that these are the highest reduction potentials. And remember, that means the highest likelihood or the highest ability to be reduced or to gain electrons. So these are the most likely to be reduced. At the bottom, these are the lowest reduction potentials. So these are the least likely to be reduced. And if they're the least likely to be reduced, that means they are the most likely to be oxidized. So if you are comparing two elements on here, or two substances, and you want to know which one's oxidized, which one's reduced, you look at the reduction potentials. And so in our example, we wanted to look at silver and magnesium. So you want to try to find silver and magnesium here. So here's silver. And here's magnesium all the way at the bottom. And so if you look at the reduction potentials, silver has a higher number than the magnesium does. So that means silver has a higher reduction potential, and so it is more likely to be reduced compared to magnesium. Magnesium has a lower reduction potential. It's less likely to be reduced. It is more likely to be oxidized. So the one with the higher reduction potential, that's going to be reduced. The one with the lower reduction potential, that's going to be oxidized. So here I have the same table from before, just the silver and the magnesium, because those are the ones that I'm interested in. And we said that the silver is going to be reduced, the magnesium is going to be oxidized, because the silver has a higher reduction potential. So we said that to build your cell, you need the two metals, and we said that the anode is where oxidation occurs, and that's negative. Cathode is where reduction occurs, and that's your positive. We put the two metals there. And so we talked about silver is going to be reduced, so that means that is at the cathode where the reduction occurs. And so this is a piece of silver. The magnesium is being oxidized, so that would be at the anode where oxidation occurs. So this is a piece of magnesium. So you put the two metals in there. The second thing that you need is two solutions. But not any solutions. You want solutions that contain your metal cations. Solutions that contain your metal cations. What does that mean? So that means that you put the magnesium in a solution that contains the metal cations, the magnesium cations. So you find a salt or an ionic substance that has magnesium in it. You can use magnesium nitrate, magnesium sulfate, magnesium chloride, magnesium acetate. Whatever magnesium salt that you have, you dissolve it in water and that makes a solution. You put it in there. Usually, however, we use nitrate solutions because nitrates are always soluble. They will never precipitate, so they'll never react with something to form a precipitate and interfere in your reaction. And so we usually use nitrates. And so in this case, we'd use magnesium nitrate. Magnesium nitrate would have Mg2 pluses and NO3 minuses floating in the solution. Same thing for the cathode. So you have a piece of silver, so you put that in silver nitrate, which has silver ions and nitrate ions. Next thing you need is a wire. So you need two metals, two solutions, and a wire. The wire is used to connect the two pieces of metal. And so usually you draw two lines and in between them you put a circle with a V. The V stands for voltmeter. So it's just a device that measures voltage just to detect that you do have a current. Since, we're doing electrochemistry and redox reactions, we want to actually look at the reactions for what is going on. And so we want to write out our reactions here. So let's start with the magnesium. So the magnesium is being oxidized. That means its charge is going up. So we have magnesium being oxidized. So does the Mg2 plus turn into Mg, or does the Mg turn into Mg2 plus? In other words, when I write my reaction, which one is my reactant and which one is my product? Well, if it's oxidized, the charge is going up, so that means you go from low charge to higher charge. So you would go from 0 to +2. So the neutral magnesium would turn into Mg2 plus, and then you would want to lose the 2 electrons there. All right, for the other side, for the cathode, we have reduction going on. So we have Ag plus and Ag. So reduction means your charge goes down. So you'd want to go with the high charge to the low charge. So in that case, it would be the Ag plus going to neutral Ag. And in this case, you'd need an electron on that side. Now, hopefully you can figure this out on your own. But let's say you're in a hurry or you get stuck. All you can do is you can just copy these down. Those reactions right here, these are all reduction reactions. And so for the reduction equation, you can just copy it down. Ag plus plus an electron yields Ag. Ag plus plus an electron yields Ag. For the magnesium one, this is a reduction equation, but the magnesium is getting oxidized. No problem, just flip the reaction. If it's being reduced, flip it, it's going to give you the oxidation reaction. So if you flip this reaction, you'd get Mg yields Mg2 plus 2 electrons, which is what we came up with. So you can come up with the reaction, or you can just copy them down. Just be careful that if it's reduction, you keep it as is. If it's oxidation, you flip it. Let's also write the potentials here. And so the potential for this one from the table, E was 0.80 volts. For this one, the potential was negative 2.37. But that's for reduction. If we flip it, if we flip the equation, we also flip the potential, so it becomes positive 2.37 volts. So again, you just use what's on your table here. If it's reduction, you write the reaction as is, and you write the voltage as is. If it's oxidation, you flip the reaction, and you also flip the voltage, or their potential. So what does all this mean? Let's look. Let's start with the magnesium reaction here. So it's saying that magnesium turns into Mg2 plus and 2 electrons. So this piece of metal undergoes oxidation. It turns into Mg2 plus and electrons. So the Mg2 plus just goes into the solution with the rest of the Mg2 pluses. And the electrons, guess where those go? Those go through the wire. And so you have your electrons going this way towards the cathode. So again, your magnesium turns into Mg2 plus and electrons. So this piece of magnesium turns into Mg2 plus. The Mg2 plus just goes into the solution, dissolves, and then electrons which flow through the wire. So as time goes by, this piece of magnesium gets smaller and smaller and smaller as it reacts until it all gets used up. In that case, the battery stops, there's no more flow of electrons, the battery dies. And also, as time goes by, the magnesium ion concentration is increasing because you're forming more and more Mg2 plus. Okay, let's look at the other side. Right here, we have Ag plus. That Ag plus is coming from the ions that are in the solution, plus an electron. Where are the electrons coming from? Yep, they're coming from the wire from the magnesium. And so the electrons that are coming through combine with the silver ions, and together they form Ag neutral. So they basically form metallic silver. And so as time goes by, these ions get used up, get smaller and smaller and smaller. Their concentration gets smaller until they all get used up. In that case, the battery stops, it dies. And as time goes by, this piece of silver gets larger and larger and larger. So overall, the magnesium turns into magnesium ions that go into the solution and electrons that travel through the wire. They get to the silver. The electrons combine with the silver ions to form neutral silver. And so the flow of electrons is what electricity is. And so that's a battery. There's one problem with that. Problem is, if one magnesium atom undergoes oxidation and turns into Mg2 pluses and 2 electrons, the Mg2 pluses go in here into the anode, and so you're adding positive charge. You're adding a positive 2 charge. You're building up positive charge in your anode. And the electrons flow through the wire to get to the cathode, and electrons are negative, so you're building up a negative charge in the cathode. So you're making this negative and this positive. Electrons are negative. They will never travel towards the positive. They will never travel towards the negative, and you're building up the negative charge here because you're putting the electrons here and you're putting the Mg2 pluses here. So now this is positive and this is negative. The electrons will want to go backwards. They're going to want to go towards the magnesium, not away from it. And so your battery is not going to run unless you add one more thing, which is something called a salt bridge. A salt bridge is something that can carry ions. So typically in the lab, the salt bridge is basically a piece of filter paper that you dip in some salt solution, some ionic solution. In AP Chem, when I did a demo for them last year, I used a hot dog. The hot dog has water in it, and it has salt in it, and so it has a salt solution. So it functioned as a salt bridge. So let me show you what the salt bridge does. So the salt bridge is something that connects the two half cells there. There's your salt bridge. And usually you can use like a glass tube that has solution in it, or like I said, a piece of filter paper that's dipped in some salt solution. A lot of times we use filter paper that's dipped in KNO3, either potassium nitrate or sodium nitrate, because both K pluses and NO3 minuses don't really react with anything because they're so soluble, and so those would just be spectators basically. So if you were to dip it like in KNO3 and you put it through there, what happens is the anions, the NO3 minuses, will start traveling this way. So what's happening here is the electrons that are negative are going from the anode to the cathode, but then in return, the nitrates, which are negative, are going from the cathode to the anode. So some negatives are going this way, some negatives are going that way, so they balance each other out, and the battery keeps going. So this is a picture of what is happening in that electrochemical cell or in that battery. Now you need to be able to draw this. You also need to be able to answer these 12 questions about an electrochemical cell. So let's try to answer those questions together. Number 1 says, which metal undergoes reduction? So we said reduction happens at the cathode. That would be your silver. So that's silver. Which metal undergoes oxidation? That would be your magnesium. Number 3 says, which metal is the anode? We said that would be the magnesium. And which metal is the cathode? We said that would be the silver from the picture above. 5 says, write the reduction half reaction and the potential. And so we already did that. It's right here. But I'll write it anyways. So number 5, you have Ag plus an electron yields Ag, and your potential is positive 0.80 volts. For number 6, it wants the oxidation half reaction and the potential, so that's this one right here. I'll rewrite it. So Mg yields Mg2 plus 2 electrons. Your voltage would be positive 2.37 volts. Okay, number 7 says we want to write the overall reaction and the overall cell potential. So we talked about that, the magnesium is losing the electrons, and then the silver's grabbing those electrons. So this one's losing the electrons, this one's gaining the electron. The oxidation and the reduction are happening simultaneously. And so we want to put these two reactions together to show the redox reaction. If you remember when we did balancing in step 2, we would split the reaction into the two half reactions, the oxidation and the reduction, and then in step 7 we combine them back again. And so these are your two half reactions, and so now we need to combine them. So if you remember, before we would combine them, we wanted to make sure that our electrons are equal. So there's 2 electrons here, there's 1 electron there, so that means you want to multiply this reaction by 2. Now when you multiply it by 2, you do not change the potential. That is not multiplied by 2, that stays the same. So this becomes 2 electrons plus 2 Ag plus yields 2 Ag. Then we combine them together, so that means we want to put the reactants together and then the products together. So let's rewrite that. So that would be Mg plus 2 electrons plus 2Ag plus yields Mg2 plus 2 electrons plus 2Ag. If you did it right, you always cross out your electrons. And so I'll just rewrite that. So Mg plus 2Ag plus yields Mg2 plus 2Ag. So that is part of the answer to number 7. I'll rewrite it just for fun. Mg plus 2Ag plus yields Mg2 plus 2Ag. For your potential, the overall cell potential, what that means is the voltage of the battery. And to find that, all you do is you just add these two up together. And so if you add those two together, you get 3.17 volts. So that's almost equivalent to 2 AA batteries. All right, number 8, how many electrons are transferred? And so you figure that out either from each of the half reactions after you've balanced them and multiplied. So 2 or 2, or you can look at the overall one where whatever you canceled. So 2 electrons. So the answer to that is 2 electrons. The polarity of the anode is negative. The polarity of the cathode is positive. The direction that the electrons flow, that's always from anode to cathode, or you can say in this case from magnesium to silver. And then the last question is asking what is the direction of the anions. So those are the nitrates that we have here, so they are going from cathode to anode, or you can say from the silver to the magnesium half cells. So I'll say cathode to anode. So for an electrochemical cell, you need to know how to draw it, and then you also need to be able to answer these questions. And that is it for the chapter. Have a great rest of your day.